Some environments do not forgive mistakes. They do not allow second chances. They do not slowly degrade machines. They destroy them. Extreme cold that turns fuel into sludge and drains batteries to zero. Deep ocean pressure that crushes weak structures without warning. Airspace saturated with cheap drones, overwhelming traditional defenses. Detection systems that punish even the smallest signature error. Most military equipment is designed for performance. Very little is designed for survival. This video is about the systems that were engineered for failure zones. Places where ordinary machines stop functioning long before the mission even begins. These are not theoretical concepts. They are real systems, built specifically to keep working when conditions eliminate everything else. Let's begin. 10. Directed energy weapons. Directed energy weapons transform air defense, especially against drones. Instead of costly interceptors, they use concentrated energy, like lasers or microwaves, to disable targets. The main advantage is cost efficiency. A missile may cost hundreds of thousands, while drones cost only a few hundred. These systems rely on electricity and cooling, allowing repeated low-cost engagements. Under clear conditions and stable tracking, they can fry electronics, disrupt flight systems, or disable sensors in seconds. Limitations include weather, dust, heat management, and line-of-sight requirements. Directed energy weapons are precision tools that enhance layered defenses, extending endurance and reducing operational costs rather than replacing traditional interceptors. 9. Electronic warfare, jammers. Electronic warfare jammers exploit drones' reliance on signals. Drones depend on radio links for control and video, and satellite navigation for positioning. Jamming or denying these signals causes drones to drift, lose control, hover, or return home. Their main advantage is scalability. A single jammer can affect multiple drones simultaneously, making them effective against swarms. Success depends on frequency, agility, terrain, antenna placement, and power management. Modern drones may adapt using autonomous fallback or frequency hopping, making this a dynamic contest. EW does not destroy targets, but denies their usefulness. In modern conflicts, denial can be as effective as destruction, saving resources and increasing defensive efficiency. 8. Radar-absorbing materials. Radar-absorbing materials, RAM, reduce radar reflections, lowering detectability at specific frequencies and angles. They do not make aircraft invisible. Their purpose is to delay detection. By weakening radar returns, RAM shortens detection ranges, reduces tracking quality, and limits engagement windows, giving stealth platforms time to maneuver, strike, or disengage. RAM is only effective within a broader system, including airframe geometry, edge alignment, engine inlets, surface continuity, and tactical planning. Maintenance is critical, as wear, abrasion, or environmental exposure can degrade performance. Despite limitations, RAM is vital in sensor-heavy environments. It does not guarantee safety but provides extra time, which is crucial in contested airspace. 7. Infrared signature suppression. Infrared systems reduce the heat contrast that heat-seeking threats exploit. Engines, exhaust, and heated surfaces create strong thermal signatures visible to sensors. Suppression techniques mix exhaust with cooler air, shield hot components, and spread heat over larger surfaces, making the aircraft less conspicuous. Reduced infrared signatures force threats closer before locking on, shortening high-confidence tracking windows and increasing countermeasure effectiveness. This is crucial for helicopters and low-altitude aircraft near ground-based threats with complex thermal backgrounds. Infrared suppression does not make aircraft invisible. It improves survivability by increasing operational margins. In hostile environments, even small advantages can determine success or failure. 6. Anechoic coatings. In underwater operations, sound is vision. Active sonar detects objects by reflected echoes. Anechoic coatings, applied as tiles to submarine hulls, absorb and scatter sonar energy, weakening signals and complicating detection. Effectiveness depends on hull condition, speed, depth, water layers, and background noise. Anechoic tiles do not make submarines silent, but reduce detectability. In modern undersea warfare, even small decibel reductions can determine whether a submarine is ignored as noise or flagged as a threat. 5. Autonomous underwater gliders. Autonomous gliders move underwater using buoyancy and glide angles instead of propellers, trading speed for endurance. They can stay deployed for weeks or months while consuming minimal power. Quiet operation keeps acoustic signatures low, making detection difficult. These gliders are designed for persistent presence rather than rapid response. They provide situational awareness, monitor maritime activity, and map ocean conditions where human or vehicle presence is impractical. In high-risk or remote environments, endurance outweighs speed. Gliders quietly observe rather than dominate, offering valuable intelligence and continuous monitoring over extended periods without revealing their presence, making them critical for long-term ocean surveillance. 4. Saturation diving systems. Saturation diving allows humans to work safely at extreme depths. Traditional diving requires repeated decompression, which is dangerous and time-consuming. Saturation systems keep divers under constant pressure in chambers, allowing travel to work sites in pressurized bells without multiple decompressions. Decompression occurs only once, at the mission's end. This enables sustained deep-water operations impossible with conventional methods, supporting construction, maintenance, and repair in challenging environments. Although complex, slow, and expensive, saturation diving ensures diver safety while allowing extended underwater missions. In deep pressure zones, it is the only practical solution for humans to operate efficiently and safely for long durations. 3. Extreme cold engine systems. Extreme cold can prevent engines from starting due to thickened lubricants, stiff seals, and poor fuel behavior. Extreme cold engine systems address these issues with preheaters for engine blocks, fluids, and intake air, along with controlled startup protocols to reduce mechanical stress. These systems ensure vehicles remain operational in Arctic or high-altitude environments where unprepared engines would fail. Reliable cold start performance is essential for mobility, logistics, and mission success. Without it, operations halt before engagement. These systems are not performance upgrades. They are enablers, guaranteeing that vehicles function under extreme conditions, allowing forces to respond and maneuver when failure would otherwise immobilize them. 2. Extreme cold battery systems. Cold temperatures reduce battery efficiency, limiting power for sensors, communications, navigation, and command systems. Extreme cold battery systems use specialized chemistries, insulation, and active thermal management to maintain output and stability. They ensure electronics remain operational in sub-zero environments, preserving situational awareness and control. Vehicles may move but are useless if batteries fail. Cold destroys power silently. These systems prevent that, maintaining information flow and operational capability. 1. Arctic articulated carriers. Arctic articulated carriers are vehicles designed for extreme cold. They use two linked sections with articulated steering to distribute weight and maintain traction over snow, slush, ice, or muskeg. Low ground pressure prevents sinking, while articulation preserves stability on uneven terrain. Where rigid vehicles get stuck or lose control, these carriers keep moving. Mobility is critical in polar regions for logistics, evacuation, construction, and sustained presence. These vehicles are not fast or elegant. They prioritize reliability and survival. 10 systems. 4 failure zones. Drone saturation, stealth detection, deep sea pressure, Arctic cold. The pattern is clear. Firepower matters, but reliability decides outcomes when environments turn hostile. If you want a deeper breakdown of any system, comment below. And if you want part 2, subscribe. Because the hardest environments are where engineering matters most.